Hey everyone, welcome to Calculus Lecture number 5, summer 2020. We've been talking about limits, one-sided limits, infinite limits, and we're about to move into the final section of our treatment of limits by themselves. What we're going to talk about today is asymptotes. And yes, this is an S. Let's take a look at the definition. The line L is an asymptote of the graph of f of x if, as we move along the graph of f of x, the graph of f of x gets closer and closer to the line L. Or in other words, the graph of f of x gets arbitrarily close to the line L. And in this case, we also say that the graph of f of x is asymptotic to the line L. Now let's review this definition for a second. We use the term asymptote in connection with the graph of f of x, the graph of a function f of x. Also, the asymptote or an asymptote of the graph of f of x is a line. Now, do all functions and all graphs of functions have asymptotes? The answer is no. Some graphs of functions have asymptotes, some don't. So the graph of f of x has an asymptote L if this line L is such that as we move along the graph of f of x, the graph of f of x gets closer and closer to the line L. As we move along the graph of f of x, the graph of f of x becomes arbitrarily close to the line L. Now, this is a heck of a definition to have to digest without some pictures. So, let's dispense with the definition and go to some pictures that will give us some real insight. Here's a good example. The function f of x equals x over x minus 2. And this graph has a couple of asymptotes. Look at the line, the vertical line, x equals 2. Notice that every point on this line is such that it has an x-coordinate of x equal 2. And in particular, this vertical line intersects the x-axis at x equal 2. The equation of this vertical line that passes through 2 on the x-axis, x equal 2. Now notice something about this vertical line, x equal 2. If I move along the graph of f of x in this manner, notice that the graph of x gets closer and closer and closer to the line x equal 2. So as I move along the graph in this direction, the graph gets closer and closer and closer to this vertical line, x equal 2. And you know what? If I move along this part of the graph in this direction, again, the graph of the function is going to get closer and closer and closer to this vertical line x equal 2. So the line x equal 2 must be an asymptote of the graph of f of x. And since the line x equal 2 is a vertical line, we call it a vertical asymptote. Well, what do you think? Does this graph have any other asymptotes? What about this horizontal line right here? This horizontal line that crosses the y-axis at the point y equal 1. Every point on this line, y equal 1, is such that it has a y coordinate of 1. So the equation of this horizontal line is y equal 1. Notice something. If I start on this portion of the graph and move along the graph in this direction, the graph gets closer and closer and closer to the line y equal 1. If I start, let's say, right here on the graph, and I move along the graph in this direction, the graph gets closer and closer and closer to this line y equal 1. And if I start on this portion of the graph and move in this direction, the graph again gets closer and closer and closer to this horizontal line y equal 1. So the line y equal 1 is an asymptote of our graph. And since the line y equal 1 is a horizontal line, we call it a horizontal asymptote. So this graph has two asymptotes. Some graphs don't have any, some graphs have one. This one has two. Now this is a good example for showing us what an asymptote is. And I think by now we probably get the idea of what an asymptote is. What we want to look at now are any features of the definition of this function that might indicate to us that the graph has asymptotes. For example, the line x equal 2 is a vertical asymptote of this function. X equal 2, we have a vertical asymptote at x equal 2. Is there anything about the definition of this function f of x that might lead us to believe that something noteworthy is going to happen at x equal 2? What do you think? I'll tell you what catches my eye. I look at the definition of this function, and from the time I was, I don't know, 5th, 6th, 7th grade, I was always told you can't divide by 0. And I look at the definition of this function and I see right away that x can't equal 2, because if x equals 2, we have division by 0. And dividing by 0 is the one thing in mathematics that we can't do. If we divide by 0, the entire world gets sucked into a black hole and nobody ever hears from us ever again. Terrible things happen when we divide by 0. So when x equals 2, we have division by 0. And coincidentally or not so coincidentally, the vertical asymptote of the graph occurs at x equal 2. That value of x that causes division by 0. This is something worth noting. The vertical asymptote occurs at a value of x that causes division by 0. What do I have to say about this? It's not a coincidence. See, all of the vertical asymptotes that we encounter in Cal 1 will occur at x values that cause division by 0. Okay. So if we're looking at a graph and trying to find out where, if any place, it has a vertical asymptote, we're going to go right to those x values where we have division by 0. Now, there is something else that happens at x equal 2 besides division by 0. Notice that if x approaches 2 from the left, my foot. as x approaches 2 from the right, and we move along the graph in such a way that x approaches 2 from the right, f of x goes to positive infinity, right? If we move along the graph in such a way that x approaches 2 from the right, f of x goes to infinity. Now, if I move this way, I'm approaching x equal 2 from the left. And if I move along the graph in such a way that x approaches 2 from the left, f of x goes to negative infinity. This is not a coincidence either. As x approaches 2 from the left, f of x goes to negative infinity. In other words, the limit as x approaches 2 from the left equals negative infinity. As x approaches 2 from the right, f of x goes to positive infinity. So in other words, the limit as x approaches 2 from the right of f of x equals positive infinity. These are not coincidences. So the point I'm establishing here, and let me get out of the way and let you take a look at the board for 5 or 10 seconds before I continue. Okay. If the line x equals c is a vertical asymptote, then the one-sided limits as x approaches c are infinite. They're either going to be plus or minus infinity. Now, do they have to be of opposite sign? Here, one of the one-sided limits went to negative infinity, one went to positive infinity. Does it always have to happen that way? No. It could be that both one-sided limits go to infinity. It could be that both one-sided limits both go to negative infinity. Or it could be that one goes to positive infinity and one goes to negative infinity. But if the line x equals c is a vertical asymptote, then the one-sided limits as x approaches c, and let me put a comma here, the one-sided limits as x approaches c are infinite. They're going to be plus or minus infinity. Now, I will tell you this. Doing all of this for the sake of intuition, and after I finish with this example, we are going to go back and consolidate everything that we've learned into a how-to tutorial on how to find and graph asymptotes. Now, we've milked vertical asymptotes for just about all that they're worth. So now, let's do the same thing with the horizontal asymptotes and see what relevant observations we can make. The horizontal asymptote is the line y equal 1. And notice right around here, close to the origin, the graph is not necessarily close to the horizontal asymptote. But where is it that the graph of f of x really starts to get close to the horizontal asymptote? Where is it that the graph of f of x really starts to get close to the horizontal asymptote? Isn't it out here where x is approaching infinity? Or isn't it over here where x is approaching negative infinity? So that's an observation we need to make. So generally speaking, the graph doesn't have to get close to the horizontal asymptote until either x starts approaching positive infinity or as x starts approaching negative infinity. And note something about f of x, the y value of the function. As x goes to positive or negative infinity. As x is going to positive infinity, what are the y coordinates on the graph doing? Aren't the y coordinates of the points on the graph getting really, really close to the y coordinate of this line, which is y equal 1? As we move along the graph in such a way that x goes to infinity, the y coordinates of the points on the graph get closer and closer to 1. And the significance of this 1 here is that it happens to be the y value of the points on the horizontal asymptote. So as x goes to plus infinity and as x goes to minus infinity, whoops, 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 whoops. Never mind, this was right the way it was. This is what we're saying. As x approaches plus infinity, the y or f of x value gets closer and closer to 1, which is the y coordinate of the horizontal asymptote. And the same thing is true as x approaches negative infinity. As x approaches negative infinity, the y coordinates of the point on this graph are darn close to y equal 1. The y coordinate of the points on the asymptote. And the significance of the 1 here again, that's the y value. It's the y value of the horizontal asymptote. Okay, first step in finding vertical asymptotes. Remember, where was it that our vertical asymptote occurred in the example? In the example, didn't the vertical asymptote occur at that value of x that did what? It caused division by 0, right? And in Cal 1, our vertical asymptotes are all going to appear at x values that cause division by 0. As a matter of fact, I can think of only one function, period, where we have a vertical asymptote and there is no division by 0 there. So even outside of Cal 1, we're going to look for vertical asymptotes at those values of x that cause division by 0. So that's the first thing. We don't want to waste our time looking for vertical asymptotes where there aren't going to be any. And the only place where we're going to find vertical asymptotes are those values of x that cause division by 0. So we're going to find all these values of x that cause division by 0. And those are our possible locations for vertical asymptotes. At each of these values of x that causes division by 0, compute the one-sided limits. Whoops. That's all there is to know about vertical asymptotes. This is how we find them. And we'll go through the steps again. Find all the values of x that cause division by 0. At each value of x that causes division by 0, compute the left-sided limit, compute the right-sided limit. And if those limits are infinite, either equal to plus infinity or minus infinity, then x equal that value is a vertical asymptote. Now, if neither of these things is equal to plus or minus infinity, then x equals c sub I is not a vertical asymptote. It's that simple. That's everything that there is for us to know about computing vertical asymptotes. Now, horizontal asymptotes. Remember when we were looking at our example, the graph didn't come close to the horizontal asymptote until either x went to negative infinity or x went to positive infinity. So we're going to start off taking the limits as x goes to negative infinity and as x goes to positive infinity. Okay. I hope you're putting the pause button on now and then to take notes, because this stuff is well worth taking notes on. To find horizontal asymptotes. First thing, compute the limit of f of x as x goes to negative infinity. Compute the limit of f of x as x goes to positive infinity. Now, if these limits are a finite constant, well, what other kind of constant is there? But I emphasize the fact finite because if the limit turns out to be infinity, I don't want people saying, oh, it's infinity, that's a constant. Y equal infinity is a horizontal asymptote. Nope. If the limits are infinite, there is no horizontal asymptote. If the limits are a finite constant, for the sake of example, let's say that the limit as x approaches negative infinity of f of x equals 3, then y equal that constant, that is y equal 3, is a horizontal asymptote. If the limit of f of x as x approaches negative infinity and the limit of f of x as x approaches positive infinity are not finite constants, then there is no horizontal asymptote. Now take a look at this, write down what you need to write down, and we are going to do an example, maybe two examples. And then I'm going to turn you loose on the exercises in the textbook. So take a look at this for about 10 seconds, 15 seconds. Hit the pause button if you need to take some notes. And we're going to work an example or two. Okay, this looks like a good example. And for no other reason other than just because, I guess we'll find the vertical asymptotes first. What's the first thing that we have to do if we're looking for vertical asymptotes? Find the x values that cause division by 0, right? And to do that, we just set the denominator to 0 and see what that forces x to be. Let's see, does this thing factor? You know, I think it does. Let's see. Is that right? First thing squared, second thing squared. First times the second doubled is negative x times 2 is negative 2x. Yep, that's exactly what it is. This is the only x value that causes division by 0, x equal 1. We have one candidate and one candidate only for vertical asymptote, x equal 1. What are we going to do now? one-sided limits. Oh, did I hear somebody say one-sided limits? That's exactly right. Next, we compute the one-sided limits as x approaches this number from the left and from the right. And you remember the other day I said that when I'm computing one-sided limits, even though I don't expect to be able to cancel anything out of the numerator and denominator, I like to factor the denominator anyway. There are good reasons for doing this, and if I factor the denominator right now, that's going to help. So let me do that. Okay, there's the denominator in factored form. As x approaches 1, as x gets arbitrarily close to 1, x plus 3 is going to look like what? 4. So for all practical purposes, the numerator is 4. As x approaches 1, what happens to x minus 1? Doesn't that go to 0? But it never actually gets there because x never actually becomes equal to 1. So I'm going to put an epsilon here. An epsilon squared. Now, as x approaches 1 from the left, is x minus 1 positive or is it negative? Well, if x approaches 1 from the left, then x is to the left of 1 on the number line. So that means x is less than 1. And if we subtract 1 from both sides, that means that x minus 1 is less than 0. Okay. So as x approaches 1 from the left, x minus 1 is negative. So I'll make this a negative epsilon. But in the final analysis, who cares? We're going to square this thing anyway. So it'll become a positive epsilon squared. And what do we have here? We have positive divided by positive, so that's positive. And we have big number divided by something going to 0. Big number divided by little number. The little number is going to 0. So this is going to be infinite. Now, we have to do the other one-sided limit as well. And I'll erase some of this just to make room for the other one-sided limit. Limit as x approaches 1 from the right of x plus 3 over x squared minus 2x plus 1. And again, I want to factor the denominator. So I have x plus 3 on top, x minus 1 quantity squared on the bottom. And as x gets very close to 4, 4 my foot. As x gets very close to 1, x plus 3 is going to look like 4 for all practical purposes. And as x approaches 1, x minus 1 is going to approach 0. But it never gets to 0 because x never actually becomes equal to 1. So I'll put an epsilon here. Now, as x approaches 1 from the right, is x minus 1 positive or negative? If x approaches from the right, then x is to the right of 1 on the number line. So that means x is greater than 1. And if I subtract 1 from both sides, I get x minus 1 is greater than 0. Okay, x minus 1 is positive as x approaches 1 from the right. So I will put a positive epsilon here, and this should be squared. So I have 4. Positive epsilon squared is just epsilon squared. I got positive over positive is positive. Big number over little number goes to infinity. So those are my one-sided limits. I computed the one-sided limits as x approaches 1. Now, what do the results tell me? How do I know from these one-sided limits whether or not x equal 1 is a vertical asymptote? I'll know that x equal 1 is a vertical asymptote if the one-sided limits, what? The one-sided limits equal infinity? And they do. So I'm going to write that down. Infinite limits. Infinite limits tell us that x equal 1 is a vertical asymptote. And I'm going to write down some of this stuff over here on the side. Because I'm about to run out of board space and we still haven't found the horizontal asymptotes. So I made a list of all of the things that we had just discovered. Okay, we're back and we're ready to do the horizontal asymptotes. Now, how is it that we go about finding the horizontal asymptotes? What do we do? Check in your notes for a second and just see what it is we have to do to find the horizontal asymptotes. Okay, what is it? Step 1. Compute limits as x approaches negative infinity and as x approaches positive infinity. That's what it is. Okay, let's do it. X approaches negative infinity of x plus 3 over x squared minus 2x plus 1. Okay. Now, from the other day, do we remember the special trick that we can use when we're computing the limit of the quotient of polynomials as x goes to plus infinity or as x goes to minus infinity? And this trick only works if x is going to plus infinity or minus infinity, which in this case it is. What do? Do you remember? As x goes to minus infinity, all the terms in the numerator of lesser degree become insignificant compared to the term of highest degree. So as x goes to negative infinity, the numerator just looks like x. So that's what we write. And as x goes to negative infinity, the terms in the denominator of lesser degree become insignificant compared to the term of highest degree. So as x goes to negative infinity, the term of the denominator looks like the term of highest degree. So as x goes to negative infinity, this is really what our function looks like. And we can simplify this, can't we? So we'll have limit as x goes to negative infinity, cancel out the x's, and we have 1 over x. Okay, we got little number divided by big number. If I take one pizza and divide it among 1,000,000 people, how big is each piece going to be? Smaller than a crumb? You're right. So if we take one pizza divided by 1,000,000 people, each piece is the size of a molecule or something. It's tiny. Little number divided by big number goes to 0. And 0 is neither positive nor negative, is it? So this is just going to be 0. Now we'll let x go to positive infinity. And we do the same thing here. X is going to positive infinity. So the term of, or the terms of lesser degree become insignificant compared to the term of highest degree in both the numerator and the denominator. So we only keep the term of highest degree in the numerator and the term of highest degree in the denominator. And we simplify from there. Well, here we go again. X, the denominator, is going to infinity. We've got a small number divided by something very large, x. X is going to infinity. So little number divided by big number, that's going to go to 0. Okay, we computed the one-sided limits as x approaches, we computed the limits as x approaches negative infinity and as x approaches positive infinity. And they're both 0. What does that tell us? When we compute these limits, how do we know whether we have a horizontal asymptote or not? The defining criteria was this, wasn't it? If the two limits turn out to be a finite constant, then that finite constant, or y equal that finite constant, is the horizontal asymptote. Is 0 a constant? It sure is. Just like 1 or 2 or -3, it's a finite constant. So we are in luck. We have a horizontal asymptote. So whatever horizontal and vertical asymptotes there were for this function, we found them. We also have to graph f of x. But that's okay. Given the information that we've come up with, graphing f of x is not going to be a big deal. Now here's what I'm going to do. I'm going to write down all of the information that we've accumulated so far. And I'm going to use that information to sketch a graph of f of x. Vertical asymptote, I'll call that VA. And that's x equal 1. And the limit as x goes to 1 from the left of f of x is equal to plus infinity. Let's see, they were both equal to plus infinity, weren't they? So as x approaches 1 from the right of f of x, that's plus infinity. And then our horizontal asymptote, that was y equals 0. And limit as x goes to negative infinity of f of x equals 0. Limit as x goes to plus infinity of f of x equals 0. And that's all of our info. By the way, I should have drawn attention to this. How did I know that it was y equals 0 that was the horizontal asymptote instead of y equal 5 or y equal -2? Well, let's see. Remember, I had this. And what did I start with? I started with limit of f of x as x goes to negative infinity, limit as x goes to plus infinity of f of x. And the limits turned out to be 0. The limits of f of x as x approached negative infinity and positive infinity turned out to be 0. So it's no coincidence that what the limit turned out to be is what our horizontal asymptote is. Y equals 0. Where did this 0 come from? That was the limit of f of x as x went to plus infinity and minus infinity. I just wanted to sort of beat that into the ground if I could. Well, let's see, where do we start? I'll tell you what. When we were studying algebra and we graphed a function, we'd draw the x-axis and we'd draw the y-axis, and they would give us our frames of reference in the xy plane. And there's nothing wrong with that approach. At the time, that was the only, or they were the only frames of reference that we had, the x-axis and the y-axis. So it's better than nothing. But having the x-axis and the y-axis are not always the best frames of reference, because sometimes the most important features of a graph occur far away from the origin. And if we use the x and y axes as our frames of reference, we're just going to draw a picture of what the graph of f of x looks like close to the origin. So instead of necessarily using the x and y axes to draw our graphs with the vertical and horizontal asymptotes, we're going to use the vertical and horizontal asymptotes as our frames of reference, because these are important features of the graph. So we're maturing a little bit mathematically. And if we need to, we can still graph a function using the x-axis and the y-axis as our frames of reference. But we have more tools in our tool bag now. We know what asymptotes are, and asymptotes are important features of a graph. So when asymptotes exist, we use those as our frames of reference in drawing the graph. And our vertical asymptote was x equal 1. And remember, the graph of x equal a constant is a vertical line that goes through 1 on the x-axis. So I'm going to draw my vertical asymptote. Here it is, x equal 1. Well, let's see, I thought it was vertical. Okay, that's a little bit better. And I'll label it like this, x equal 1. There's my vertical asymptote. Now, I guess the joke's on me in this sense, because the horizontal asymptote is y equals 0. And y equals 0 is just another name for the x-axis, isn't it? So here's my horizontal asymptote, alias the x-axis. And I guess we're drawing the x-axis here because it is an important feature for this particular function. The x-axis, also known as y equals 0, is the horizontal asymptote of the function that we just worked with. So I've plotted my asymptotes. Now I've got to draw the graph. And we are going to use the limits, the information that we got from our limits, to tell us how to sketch this graph. First, we'll look at this limit. This tells us that as x approaches 1 from the left, f of x, the y value, goes to infinity. So here's x approaching 1 from the left, and here's f of x, the y value, going to infinity. So as x approaches 1 from the left, f of x, the y value, goes to infinity. And both of those things happen simultaneously. The net effect of x moving from left to right and y going up is that they both happen simultaneously, and the graph moves like this. Okay, that looks pretty good. Now we'll look at this guy. This limit tells us as x approaches 1 from the right, f of x, the y value, again goes to positive infinity. So here's x approaching 1 from the right. And as it does, f of x, the y value, goes to infinity. So here's y going to infinity. The net effect of both of these things happening at once is that the graph moves from right to left and it goes up like this. So that looks pretty good. Now we'll look at these limits. This tells us that as x goes to negative infinity, f of x, the y value, gets closer and closer to 0. So and remember what this horizontal asymptote is? It's y equals 0. So as x approaches negative infinity, f of x, the y value, gets closer and closer to y equals 0. In other words, the graph is going to get closer and closer to this line, y equals 0. And as x approaches positive infinity, here's x approaching positive infinity. As x approaches positive infinity, f of x, the y value, again gets closer and closer to 0. The y values, or the y coordinates of the points on this graph, get closer and closer to y equals 0. So that means that the graph just kind of snuggles up right next to the line y equals 0. And voila! We have created the graph of f of x equals x plus 3 over x squared minus 2x plus 1. And we have done our first graphing exercise with asymptotes. What do you think? Should we do another example? I think so. This will be the end of the end of lecture number 5, part 1. And we'll have a part 2 where we'll do another example with vertical and horizontal asymptotes.